I gain a lot of, oh, I thought I had the website up. Apparently not. Yeah. All right. Now I'll relog back in. Please don't make me do that again. Okay, good. So let me see how he arranges things after Bernoulli's equation so that I kind of am falling, into the correct sequence that he determined. So kind of we're done with Bernoulli's equation. We got that problem. I went ahead and put that on there. But let's see what. Okay, so it's coming up where we were. Okay, so we go to here. Okay, there's Bernoulli's equation. Application of Bernoulli's equation. A bunch of problems. Energy and hydraulic grade lines. And so those are just, okay, so let me see after that. The energy equation, which is the similar things. What has he got here? Okay, so let me see. 5, 11, 12, and fundamentals and conceptual. Okay. So let me go back to this one and let's see what he's adding to this. Oh, he's doing thermo, I think. Yeah, he's doing thermo. So he's doing internal energies here. So to me, yeah, there's his internal. So actually, this is best left into thermo because that's actually thermo. Okay, there's this thing working it. So I'm just going to skip that section, but you've already done that in thermo or are currently doing it. Yeah, so there's all of his stuff. So I think he's adding that just to be complete. Okay. Energy and hydraulic grain lines are kind of like the concept that civils love so much is that, let me see if I can find, usually there's a picture. There you go. So what you got is visually, you can see, how do I do this? Oh, I know. Visually, you see, make sure I get all of those. Visually, see the energy line, which is basically all the terms. For a civil, they love it this way. So that's all those numbers all added up. And if there are no losses, it just remains the same throughout the whole path that the particles take. If, for example, what he's doing here is he's attaching a pipe just to the side of the thing, then you're getting all the energy except that. Then if you put the thing so it stagnates here, it goes all the way up to the energy line. Meaning that you've taken that kinetic energy, which was here, and then bam, you took it all out and it just shoved the liquid up further because it stagnated, or it basically drew the velocity down to nothing right here. And as a result, it increased the pressure this much from that. And then what happens is you go uphill a little bit, and he shows it kind of widening the pipe. And this kind of reduces because you widen the pipe and the flow went from this speed to like that speed. And then You do the same thing, you ram it against there, and you should get that same level. But if it's a long enough piece of pipe and you're looking at a real situation, you know, your energy line, you're losing a little energy as you go. Your hydraulic grade line will be down a little bit. And so essentially, the real world is that energy grade line is not constant. And that'll be the point of the later chapter. So in essence, that's all it is. It talks about the hydraulic grade line, which is this thing. Let's see. That thing. And then his hydraulic head, which is the term without the velocity. And then he just goes on and okay, so now he's drawing this thing out. So a civil engineer looks at things like this. However, a mechanical should as well, really, which is kind of convenient if you're looking at the equations with that have the v squared over 2g and the elevation. So the way this is the form that we kind of like, because it's units of feet, and so visually you look at it and it's feet. How much energy above that? What's kind of cool about that is, let's say you had this. You took this as a new, let's see, you did something like that. You went down, you created something, pipe system. It does all that. Everything's great. And then what you do is you make it go down the pipe and into a reservoir. And it turns out you'll find the reservoir will be at exactly that location. So it basically, the energy, the kinetic energy dumps to nothing. The pressure at the thing is zero. And that's where the energy ends up being. So the next question would be, he said, he's got some videos in there. There's something interesting we should look at sometime, but maybe okay, work energy, we get through here. What does he say? Chapter 5. I'm sorry, chapter 6. Did I get there? Oh, I am there. Linear momentum. Hello. Gosh, it's slow. Okay, doesn't look that way. Okay, maybe it does look that way. So he starts looking at equations that were similar. So this is the part where he did a mass thing before, and now we're going to do a momentum. So if you look at these equations, he has done them. We've already done these. I don't know if there's a memory of it, but before we had, so if you look at this equation, this is called Reynolds transport. And before n, okay, so the little n, this term, is equal to the big N per unit mass. So before, what we had done is we had taken that equation, and if you did dm, change in mass of the system, it's basically equal to this plus the integral across the control surface of rho v dot dA. which this breaks down to m dot in equal to m dot out. That's essentially what that breaks down to. Now, he's going to add an extra term, basically the velocity, and you'll see it gets stuck in there. And so what happens is this becomes sum of the forces equals to these terms, essentially this. So it becomes a momentum equation. And he goes in and does this. We should do some discussion about it. Okay, so he says the sum of the forces is equal to the low. I'm not sure I buy completely into those two descriptions he's got. The one on the left is the time-dependent change. The one on the right is not. For steady flow, the one in the middle, local momentum changes, becomes zero, and you just get steady flow. And if you have steady flow in which you can integrate across and find your averages, you can get this. And you basically can sum the forces on something and work out what the force would be. Let me see if he's got a good example. Let's see what he's got. Hopefully he has a good one. If not, I'll go look for one in the back of it, in the problem set, which I guess I should have just done that. Okay. That's a weird picture. No, I don't know what he's got here. Okay. Let me just go find a good problem. Okay. Problems. Maybe I should see fundamental problem. I wonder what the fundamental problems look like. I think the fundamental problems all had solutions. Okay, that's no fun. That's no fun. That's no fun. That's no fun. Well, that one might be interesting. I guess for lack of a better thing, let's see what this is. Now, I gotta find a really good one. Oh, here we go. This is probably good. Unless there's a better one. That if there's a better one, we'll figure it out later. We'll look later for a better one. So it says, oh, oil flows through the 8-inch diameter pipe, which is right here, at 18 meters per second, and if it discharges in the atmosphere through the nozzle, determine the total force of the bolts. Determine the total force the bolts must resist at the connection AB to hold the nozzle onto the pipe. 2 or 3 things he hadn't described here. First thing, he should have said no losses. Because here's what we'll do. So if it's 18 meters per second there, I'm going to write Bernoulli's equation. I guess I'm not going to say AB. I'm going to say location 1 and location 2. So I'm going to say P1 over gamma plus Z1 plus V1 squared over 2G minus no losses equals to P2 over gamma plus Z2 plus V2 squared over 2G. If it's an 8-inch diameter pipe, Then 18 times pi 8, and it doesn't really matter whether I divide by 12 squared is equal to V2 times pi times 4 squared over 4. Go ahead and cancel those, cancel that, and then V2 be 18. 8 squared over 4 squared, which actually is just 2 squared. But you know what? I'm gonna try this again. Okay, let's try it again. This will be funny. Photo math. Let's see if it'll work. Let's see if it'll give me the answer. Well, it wrote it out right. Okay. So end up. Wait a minute. Did it? Oh, it did do it right, and I wrote the wrong thing there. That's funny. That's hilarious. Let's see if it'll do it again. This time, it copied it 8. Oh, it forgot the 18. That's not the actual thing. Oh, can you? You know what? Let me move the 1 closer right there. Let's see about that. Ah, okay. Okay, so that's what I get coming out. He goofed us. We use meters, inches, but you know what? It doesn't matter. Yeah. So what he did is meters per second, okay, feet per second, okay, inches. So he's got some issues there. So I think this is supposed to be feet right there. But anyway, I get a velocity coming out of 72. So P1 is unknown. Gamma, okay, so he's saying take gamma, the oil, to be that. 55 plus the Z1 and the Z2 will make the same. V1 was 18, but now, okay, it's 18 there. 18 squared over 2, 32.2, equals to P2 at the exit is 0. So V2 is going to be 72 squared 2 over 32.2. So I'm going to get a pressure back here of 1 of equaling to 55. I'm going to try to make my handwriting really good. 72 squared over 2, 32.2 minus 18 squared over 2 times 32.2. Okay, I think I did my handwriting okay. Let's see what it says. Survey said. First, let's see if it recognizes it. I think I got it. Okay, I got 4150.6 pounds per square foot. 32. Yeah, 1872.55. Yeah. Yeah, that's a typo. Because I think what he did is he said it right here, and he put the drawing right here. So I think, this was kind of one of those things where it just got, it just, yeah, yeah. And this is the book is only in its second edition. So I think, the other fluid book I was using was in like the ninth edition. So it had several cycles to get fixed. Usually you'll find about the third or fourth editions, all those errors get pulled out. Yeah. Okay, so we got all that. And that actually only gave us, okay, let's see if I can get this to work. That only gave us the pressure. So at this point, we have pressure here equals 0, pressure here equal to 4150.6. pounds per foot squared. If we wanted to, what's that? 4150.6 divided by 144 gives us 28.82 psi. So that's the pressure I got right there. Now we're dealing with finding the forces or things that are held by those bolts. So if you look at this, sum of the forces in the x direction equals the sum over the control surfaces of Vx rho V dot A. So notice something interesting here. What's really, I think, really interesting is this is m dot, and that's all it is. So if you multiply m dot times the velocity, that's the momentum. So if you think back to dynamics, okay, this is a side issue, but it is and it isn't. Sum of the forces equal to this mv dt. And so now, if you look at it, there is something very similar here going on here. And what's similar is if you operate that on this portion, m dot times v, it's the same kind of thing that happens up here. So in fact, it's the same thing. It's the same equation, just looked at and thought about a little bit differently. So all you got to do now is go in here and say, okay, what's my control surface? Here's my control volume, and it sits like this. Here's my control volume, and you technically want to do this. You want to do this, pull that down here, then you want to do a copy and a paste, and you want to look at them and say, what's the forces? Put the forces on the left one. I got a force here of pressure times area. So essentially, what you're getting is, here's your equal sign, and all your forces are listed here, and all these other terms are listed there. On this, you have 18 feet per second, and then you have 72 feet per second. Oop, that's not that, that's this. On the left, you have that. Now, you technically also have that, but, your weight, but nobody's summing in the y direction, so, yeah. So, you don't have technically you have a force here. You have the pressure exit, or pressure at the exit times area, but the pressure at the exit's 0. Now, the next thing you got is the metal jacket is holding this edge so that it it doesn't like blow up into space, so to speak. So you've actually got a force of the steel on the water. Kind of a weird way of saying it. And so that's what is transferred back up to these bolts. So if you look at the left side, you got the force of the steel on the water minus the pressure times the area equal to, and all you do is you look across these control surfaces and you do this. You have an exit here and you have an entrance here. You have an area pointing out this way, and you have an area pointing out that way. So on this one, they're going together, and this is where there's a lot of bookkeeping that takes place. Here's the bookkeeping. My my V of X is going in the negative, because really I should have put this as being positive. And that's the same thing over here. Positive will be to the right. But I've got a Vx here is actually going to the left. The next thing is this term. If you look at that term, you get, of course, rho, and I'll just leave it as rho. And V dot A, they're both going in the same direction. So what you get is 72, and then you get pi, the area. I think it was 4. Now I've got to be careful. 4 over 12 squared over 4. That's my area. So there's my rho, there's my V, and there's my area. Now, the next one I'm doing is that one. And this one, it's going to the left as well. So the Vx is going to the left. And the dot product is negative as well. So what you get is your rho, and then you get this term minus, and you get an 18 times pi, and I think it's 8 inches, 12 inches squared over 4. And so this is your velocity, this is your area, and this is because it's a dot product, meaning that they're both going in different directions. So what you get, okay, so he said the density of this thing is 55. So knowing that, I know the density of water is equal to 1.94. I mean, yeah, and I also know gamma of water is equal to 62.4, and this is slugs per cubic foot, and this is pounds. So if I need to know the density, what I need to do is I need to find the specific gravity of this oil. So the specific gravity is equal to 55 over 62.4, meaning that this is the ratio. The oil is lighter than water. And then I can multiply that times 1.4 to get myself back to get that density. So in other words, these two numbers should be 55 over 62.4. That'll give me the specific gravity times 1.94, and that's the rho of water. So this will give me the density of the oil. Let's just see. Photomath to the rescue. You don't think so? It does look funny, doesn't it? See what it does. They recognized it. How wild. 1.71. It did it. So if you want to know the force of the steel on the water that gets transferred back, I'm going to move this pressure times area over here. What I'm going to do is, since I know it's in pounds per square inch here, I'm going to say 28 and 82 pounds inches squared times the area, and I'm going to use the inches. Okay, pi 8 inches squared divided by 4. So this will be inches squared. So out of this, I should get pounds. Okay, 28 and 82 times pi 8 squared over 4 plus. So I'm going to do photo math, see if I can get that one. This shouldn't be an advertisement for that photo. See if it does it. Well, it looks like it did it. 1, 4, 4, 6, 5. Now I got to put together those other terms up here. So what I'm going to do is 1.71 is going to be multiplied times both of them. But I better do it this way. I'm going to go ahead and take the minus sign and put first. And that doesn't look like a 1, and that doesn't look like a 1. But now it kind of does. It kind of looks like a 7. And then I'll put parentheses 72 squared for both of those. And then I'll put pi times 4 over 12 squared over 4. Now I'm going to see what it'll tell me about that number. Makes classroom go faster. There we go. See if it recognizes it. I think it did recognize it. 773 and 58 with a minus sign. We'll put the minus sign even in there. And then this time I'll get 2 plus symbols. So those will go together. And then plus 18. Oh, I better put the density in there first. 1.71 times 18 squared times pi 8 over 12 squared, all that over 4. Now, you might get upset about that, so I'm going to put a bracket around it. See what that comes up with. Mm-hmm. 8 squared over 4. Oh, I think it did that too. Yeah, it did. 193.396. Now those are too far apart, I think. But I could bring them together. Here's what I'll do. I'll try to bring them close to one another. And that one goes to there. Steel on the water. Okay, let's try that. It might be able to get that all together. And without touching the other. Yeah. Yeah. Mine did that and did a fraction. It's really weird. It did 233 over 500. So at that point, how do you make it do? How do you make it do that? Why would you want to present the answer that? Huh. Maybe. Here you go. I'll mess with him. I'm gonna do that and see what it does. just out of curiosity. See what he does now. He put another fraction on there and just extended it out. Okay, let's see what happens if I do this. Or here's a good one. Oh, 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 1. Let's see what he does with that one. This will be funny. Okay, I don't think I can fit it in there. This will be funny. He still gave me a fraction. Oh my gosh. Okay. So 868 with some digits. There you go. That is hilarious. So he wants to convert it to. That's really interesting. But then above that, so above that, he puts the 4, 6, 6, right? So if that's just really weird why you would. Oh, and then okay, so then he takes that, moves the digits over. So what he's doing, here's what he's doing: 868, 466 over. Okay, 1, 2, 3, 1, 2, 3, and then he moves it back away from there and says it's 868 times 466 over 1,000. So I get it what he's doing there, but yeah.
So is that what's on the bolt?
That's what the total on the bolts, yeah.
But it didn't give us
It yeah, and technically it should. I mean, if you're really in the industry, you want to know now you want to know how many there are.
how many bolts
Yeah.
or
And
how
then
few bolts.
yeah, and then you want to go in there and pick the right bolts that'll hold the load, you know. That gets into machine dynamics or whatever that fundamentals of mechanical design. That gets into that course. So that's essentially the way you're supposed to do these problems. You're supposed to basically go in, take. I like to draw this twice. The same picture, but on the left picture I put the forces. On the right picture I put the velocities. That way, if you put them all together, sometimes it's just too much. It gets too confusing. And that's just the way it is. Oh, it's 12:43. So that one problem took us all the way. That one problem for this weekend is the shower head problem, the one we did. That's the reason I didn't say anything about it. And I did that for all the classes because I was out with the flu last week. And so I myself am not up to speed. And so I think next week I'll go back to 3 problems. Um, but the 3 problems will probably be these type of problems. Which actually, if you look back, let's see, just out of curiosity, I mean, I stopped at that. What else does he have? Well, that's a good one. That'd be a good problem to do. I guess that would be a good one to do. I'm not sure what I'm seeing there. That's a good one. That's a good one too. Although those are the same problem. That's a really good one. Yeah, that's a good one. Yeah, it looks like it's one of the ones that tries to jet the, although that's not the way they're built, but they could be built that way, where it sucks the water in and the jet comes out and gives you the propulsion. Yeah. Yeah. So we'll do some of those. Well, there you go. That's a pretty good one. The water hits the boat, although it's going to sink the boat eventually. Um, well, there's a nuclear reactor thing. There you go. There's a. So I don't know. These I didn't go far enough, but the pictures actually are pretty good. Problems look pretty reasonable. Yeah. So we'll come back in and do some of these, and we'll do some of these for next week's homework. There's a water hitting the wall. I don't even know what that is. Circular craft. There's drawn in. Oh, on the top and discharged on the ground. Determine the pressure that the craft exerts on the ground. Oh, okay. Yeah. So that's kind of what that is. There's a garden hose hitting a thingamajigger. Another garden hose hitting it. Another garden hose. A truck making 45 3-inch diameter depth of water should determine if the depth of the water in the truck is 4 feet. Determine the frictional force the road has to exert on the tires to prevent it from rolling. Oh, okay. Ooh, there you go. That's a good one. No, these are okay. These are good problems. Yeah, there's a lot of them, so we have a lot to select from. We'll go in and pick 3 of them. I'll work a bunch next time, and then time after that we'll. Okay, so here's rotational stuff. I would be interested in seeing how he presented the rotational stuff. Let's see. That is a constant angular momentum equation. Let's see what he did here. It'll be very interesting. Okay, come on. There we go. It should be R cross something. R cross F for 1. Okay, that's just pictures. Control volume. R cross MV. Okay, that's good. All right, that's good. And then R cross V, that's good. So he he did a good job there. Okay, steady flow. The key is, how is he going to determine his vector diagram? That's what I want to see. Because some people use weird terminology there. But he wrote a dynamics book, so he should not use weird terminology. That's not a turbine. I'm not interested in that. Okay, here's the turbine count. Oh, good. All right. So this is the part that I'm looking for. Velocity of the F with respect to A plus the velocity of A. You add those two together and you'll get the velocity of F. He wrote the dynamics book, so you should write it this way. That's the way you should do it. So good. I'm glad he did that. Okay. There you go. That's what I'm looking for right there. That is the way to do it. The other book uses.
But you just ultimately just sign point direction.
Yeah.
They both positive forces, just one in one direction, one.
Yeah.
And that's why you get this one pointing this one.
Yeah, in this particular case, that may be the case. What I was looking for is the fact that you have, if you really look at this, kind of here. I'll just, if you remember back when we did dynamics, here's what really bothers me about some other text presentation of this. So what he's saying here, oops, oh yeah, here we go. You know, actually, if you want to know VA with respect to F plus VF. So actually, you know, his notation is right. I'll question signs later. But if you want to know the velocity of A, you have velocity A relative to F plus velocity F. Other textbooks, I've seen this where they'll use a V, a W, and a U. And you're looking at it and you're like, okay, which one was U? Which one was W? Which one was V? So it just makes the whole problem set so hard because you don't know, you'll have to kind of think back constantly about this. Whereas if you use this notation right here, this is the velocity of the fluid. So if you have the sprinkler, you know, and it's coming out, and this thing is A, and it's spinning around at some speed, you got velocity A. Then you got the velocity of the fluid relative to A. So the velocity coming out relative to A, actually, so velocity of fluid relative to A, and then you add velocity of A to it, then you get the actual velocity of the fluid coming out of the sprinkler. And so these subscripts are very descriptive and have an understanding. You don't have to think about what's V, what was W, what was U.
So, for simplify it a little bit more, if I took my finger and held my finger behind the sprinkler and didn't let it move, I would feel the force of the fluid.
Right. What you would be doing is you would be setting that equal to 0. And that means the velocity of the fluid is the velocity of the fluid relative to A, because you made A 0. And so what happens is there's kind of an offset. If you think about it, you know, the fluid's still got to come out of the pipe, right? So when it's coming out of the pipe, you know, you're looking at it and you're seeing M dot is equal to the rho times the area of the end of that pipe plus the velocity of the fluid relative to A, because that's what's coming out of that pipe. So if this thing is spinning, all of a sudden, as it's spinning, the velocity of the fluid starts, you know, changing because it's spinning. And so, since he's used this notation, I'm going to work some of these problems now. You know, the last few years I've skipped that because I found people have a real problem with that. But now that we've got this, you know, I think that's the way you do it. You don't do it with this. So that's a positive thing. So we'll cover that this time, whereas before, you know, I had been letting that kind of slide.